Today I want to present to you a use case, a how and a why of why we chose a database to fit our data model, rather than trying to adapt our data model to our database. So with relational stores, you've pretty much taught there's one size fits all for your database, so figure out your data model and you'll be fine. And we did the opposite. So first, an overview of what we do of SoundCloud. So SoundCloud's a social platform. You can think of it like Flickr for sound or YouTube for sound. And social sounds are at our core. So these are the sounds, the little waveforms, and social activity around them, like likes and comments and favoritings, sharings. This is how the sounds propagate. And this network on our site, on our devices, and also other social networks like Facebook and Twitter. So when logging into SoundCloud, you get this page, overview of the sounds inside of the network, sounds that other creators have uploaded. And we're working hard on fine-tuning that listening experience. So if you'd like to see our next website, you can go to next.soundcloud.com and get a preview. We've seen some pretty good adoption and some success. We serve a lot and we store a lot, and there's 20 million registered users that are also helping us unmute the web. But this is going to be a talk about databases, and so after introducing SoundCloud, I want to introduce this talk. So thinking about what to present, I often go back and I say, what should I tell my past self so he can be smarter? And in this talk, I wanted to ask myself, what was the most important lesson that we learned at SoundCloud about our database usage? And save you the suspense, it's simply understand what your database does for you. So to put that in perspective, if this was a architecture, or if this conference was for building architects, that answer may come in the form of understand what your building materials do for you. And it's not too far off. In the world of structural engineering, it's still putting boxes together, maybe using concrete instead of arrows. And wanted to shine a light on a dirty little secret in our craft. Not everything works as expected. So believe it or not, much of the books that we read are coming from experience of things that don't work. But there's a definite lack of sharing these stories in the conferences like this. And I want to break out of that trend and talk about stuff that hasn't worked so well, as much as stuff that has worked. So yeah, if we're using the metaphor of building materials, we also need a metaphor of abstractions. We need these abstractions in our jobs to do our jobs effectively. We can't be laying bricks every day. But in our world of engineering, we live under the constraints of physicality. So we have space and time and the laws of physics as our core constraints as engineers. So those constraints form the base of our materials, and our abstractions form the rest. They form the art of our craft. So as an industry, we often put our blinders of abstraction on. So this means that you may be looking at your problem, or maybe looking at your source code through the facade of your IDE. You may be looking at your solutions at the stock imagery of a vendor's brochure, or you may even be looking at your architecture with boxes and arrows. They're all abstractions that help us do our jobs effectively. But it's too soon that we forget the limitations of the physical world and how that applies to the abstractions that we use. So seen with these eyes, I'm going to introduce the case study. But first, I'm going to, this case study is going to go into details somewhat in depth, but I still consider them high enough level where I feel that they're important for all of us to know. We're going to talk about Mysql. This was the data store that we use for most of our online data, and Cassandra. And this is the data store that we chose to replace Mysql for a specific use case. Databases are different things to different people. And so I'm going to limit the scope of this talk to just persistence. So I'm not going to talk about acid, atomicity, consistency, durability or transactionality, or base. I can't even remember what base stands for. I'm just going to talk about you write it, you read it, it doesn't go away. And there may be some kind of low-level details. I have time after the talk to go into more depth. I have a little bit of time before catching a plane. So I'm going to try to leave some time at the end of the talk for questions in the audience, and then I have a bit at the podium. And some of these details may be old hat for you, but whether or not, the message is still the same. Understand your materials. I'm going to use some terminology called primary storage and secondary storage. Just to clear that up, primary storage is the storage attached to your CPU. Secondary storage is the storage attached over your I/O bus. Primary storage is your RAM. Secondary storage are your disks. And the materials I'm going to be talking about are going to be spinning disks. So sometime during the talk, you may think, oh, just why are you wasting your life? Use SSDs and everything will be okay. And that's not the point. The point is, if you do use SSDs, understand them. If you don't need to go to secondary storage, understand your primary storage. If your solution fits in RAM, understand how your DRAM works, understand how your memory bus interacts with your CPU and how your CPU interacts with its caches. And if you have massive storage on the exabyte scale, if you're from Google here, your materials will be magnetic tape. So you may also think, I'm in the cloud, I don't have to worry about storage. I'm in the cloud, I don't have to worry about hardware. The cloud does the hardware for me. But the cloud's also based on the same first principles that we deal with as engineers. They're based on the same materials, and you can't ignore the hardware that runs the cloud. So the lessons learned here apply equally well as in the cloud. So the data that we're storing and serving composes our activity feed. It's the dashboard page after you log in. And this display changes when somebody in your social network either contributes or creates a social link between them and a sound, or whether they upload a sound themselves. So this is going to be the scope of the data model that we've taken out of our primary primary database and have built a specialized solution for. This feed, for the sake of the product, needs to be consistent. So if you log in once and you see these tracks, and then you log in again and the third track has disappeared, that's an inconsistent experience. And so for us, in the product development, it was very important to have that consistent experience. And that meant saving off. For us, the easiest thing that we could do is save that off beforehand and display it once you log back in. As a graph of our data model, we have viewers and creators. These are both users. There's a relation of following. There's relations to creations in the site. And then there's a transitive reduction from viewers to sounds over creators and their creations. We chose to materialize the first degree of this traversal in what we call events. There's other options when building an activity stream. You can also materialize that page on read, but we chose to materialize it on write for the goal of maintaining a consistent experience and having it load quickly. So we wanted to pre-compute all of the events so they would be ready when the next time that anybody logs in. So we wanted, our goals were latency and consistent experience. As an entity relation diagram, kind of an incomplete diagram, but this is how you can model it with, this is how you typically visualize it in a relational store. And we just took this mapping to the first degree of creations and saved that off into its own table. Yeah, this worked out really well. And there's some benefits for having this. Because at any point in time, we can go back and reconstruct the dashboard. It's also robust against changes to our algorithm. So if we say that we're going to introduce or remove creations, the prior creations don't change. And so you can maintain that consistent experience. And the event store in MySQL worked out pretty well, but we extrapolated some of our growth in the relation of how much we were storing versus how many registered accounts we were seeing. And we quickly realized that we could be in trouble. But in fact, we were actually in trouble. And we were seeing up to 2 seconds of load times for some of these dashboards, and something that we'd tried to optimize for up front by doing all this work, calculating everybody's dashboard before they even log in. And so we were baffled, like, how can we do this? We're writing fine, but we're reading slow. This is completely opposite to our intuition of what relational databases are good for. And so we sat down and we tried to understand a little bit of why this was going on. And I'm going to jump around in time in the past and actually describe what was going on, because it shouldn't have been this way. We were writing just fine because of some natural properties of our data set. So to illustrate that, the table that we were writing had a surrogate key, meaning that this was a sequence, a number sequence that was managed by the database. This sequence created an ordering that closely matched the ordering of events that were coming in. This acted like a sequential clock, and as a result, the database could use that to its advantage. Now, to understand what the database is doing for you, we need to understand how the database's storage engine interacts with the material. And by using InnoDB, storage engine, a common storage engine for MySQL, actually an awesome storage engine for MySQL, you just can throw it whatever and it's not going to lose your data. And it's optimized for a broad class of access patterns. It's really just the go-to general purpose storage engine for mutable state. And the way it manages this is it carefully balances a B tree, actually a B plus tree on disk. And this data structure has some branches, and in its leaves, it stores the records. So in InnoDB, everything's a B tree. Even the records themselves are stored as a B tree. They're actually stored in index form. And in InnoDB, the primary storage for InnoDB is a clustered index, meaning that they're ordered, the records are ordered off of the primary key. So with that sequential primary key, we get our leaves, which contain our records, grouped into pages, which contain I/O units, nicely laid out sequentially on disk. So the on-disk format, which we weren't really aware of at the time, turned out to be quite efficient. This is why we were able to accommodate so many writes per second, because we were just keeping that order and writing one after the other, adding one page after the other. But on read, we couldn't read in this order. We needed to read off of those viewer IDs that were coming in. Each viewer gets a unique index, a unique view, and as such, we needed to index our data set so that each viewer could pull out those records and we could follow the next degree of the traversals. And so InnoDB, being a super B tree, stores the index in index order in a B tree as well. And on disk, this turns out to have the exact same format. The records traversable to the leaves, into pages, with the values of the leaves being the primary key of the item that the secondary index is indexing. So what happens when adding and updating the indexes is that when as you're adding more and more items to an individual user's activity stream, it may actually fill up one of these pages. So one of these I/O units is 16 kilobytes. And if you're storing more than 16 kilobytes of primary keys in this, NODB performs a page split. It'll bump up against the next page, so there's no more room next to each other. So it'll need to go off and create a new page, typically at the end of the tree, and fill that up with your index. So this is one characteristic of B trees. When you run out of space, you need to go somewhere else. But once you do get those primary keys and you go into the clustered index, primary index, you may be loading up different pages just to get a single record out of each page. And each of the pages that you load could potentially cause a seek. Yeah, I mean, this may be a review for a lot of you, but I really want to drill it in that why seeks are important when understanding your database, because this is what got us. The database is simply an API to your storage medium that gives you some abstractions to reason about your data. But seeks are not something that we can ignore. Quickly overview: disks are spinning. You can pull data off of it or put data onto it as quickly as they're spinning. But you need to locate to where that is. And yeah, when you locate to where to put the data on the physical device, you may need to move from where you are, and that causes a seek. It's difficult to conceptualize how bad these actually are without understanding a little bit or having a mental model of time. And I think it's important for all of us to strengthen our mental model. So this is a nanosecond. And it's kind of hard to visualize because we have no sense. I mean, do you make toast and it pops out in a nanosecond, or what? There's nothing that we deal with except our computers that work in this time scale. So if we translate this time to distance, we can get a little bit more intuition about how long that actually is. So I mean, you can't go faster than the speed of light, unless you watch Damien's talk and you're using Perl. So if we go the speed of light in 1 nanosecond, that equates to the distance of about this much, about the long side of a piece of paper, about 30 centimeters. So that's a nanosecond. That's 1 nanosecond. This is the fundamental unit of our computers. This is what we're processing our code at. This is what the unit of measurement that we measure our inner functions. These are the fundamental units of our computing universe. But yet, these are the units for seek. It could take up to 10 milliseconds to seek. And so, yeah, how long is a seek relative to a nanosecond? How long is going to disk relative to staying in code? And how far could an electron travel at the speed of light in 10 milliseconds? So to give you an idea, 10 milliseconds for an electron is like going to Milan from here and coming back. So it's like a round trip to Italy to send something to your disk. And this is why we started to see those 2-second response times. So once you have a seek, you pretty much know where your bottleneck's going to be. Next thing that we saw is that it wasn't just seeks, it was also storage. So from our growth, we knew that we couldn't keep all of our events on one host. And we also knew that we were creating more and more pages for our index. And this was all for what was ultimately mostly cold data, mostly data that would never get loaded in one day. So the more storage we had, the more space, the more storage that we required, the more space between our pages that we were seeing, and the more seeks that we were incurring. And yeah, and we also knew from extrapolating our growth that we wouldn't be able to fit on one host for very much longer. So we took a 10,000-foot view, and as a reminder, we didn't know this back then. So we didn't know what I just described, and so we only had a 10,000-foot view back then. We didn't realize that what we were having was a disk problem. What we saw was we were having a database problem. The documentation about all this is tucked away on MySQL's documentation site, so we eventually did learn it. But at the time, all we saw was outgrowing our storage capacity, getting response times that were out of reason, and not having a way of mitigating it with the database that we were running on. So we had some tough questions to ask. We needed to ask ourselves, do we want to keep this materialization on write strategy? Did we want to change everything and go with the materialization on read? And then we considered the product, and we considered the amount of change that it would take to completely change the way that we were displaying the activity feed. And we said, yeah, let's stick with the materialization on write, and let's look at the databases. But before looking at the databases, we spent a little bit of time understanding our data model. And yeah, some of the properties of our data model were quite beneficial. It's eventually consistent. And by this I mean eventually consistent in that the writes are observable in the same order by any reader, but at different times. So if there's writes of A, B, and C, every reader will see A, B, and C, but they may not see A at the same time, and they may not see B at the same time. But this is fine, because we just have one reader. So if you only have one reader, everything can be eventually consistent, as long as the reader is not the writer. And on top of that, because people don't log in, not everybody logs in at the same time. It could be multiple days between logins, and so a read could happen actually much later than a write. We also knew we had hot writes. All the content's being created right now. And so if we're going to materialize that first degree of our graph, we are writing all at the same place. And no matter how fast you can go, if you have a hotspot, you're likely going to run into a bottleneck eventually. So we knew that we needed to have at least some measure to be able to distribute these writes over multiple locations. But identifying your hotspots also means that you can use some techniques. You can stay in primary storage for a little bit longer before going to secondary storage. So you can basically buffer in RAM before writing to disk. And this means that you can accept more at a higher write rate and then flush out. We also had cold reads. So most of the pages that we were rendering were going to be rendering from storage. There was no way that we could keep everybody's dashboard in RAM. This would be totally wasteful use of RAM. And we could count on the viewers, once they load their dashboard, to only load the head of the dashboard sequentially ordered by time once they find their index. We also, because we didn't want to stay with, or we wanted to avoid having hotspots on writes, and we wanted to distribute the cold reads, and we knew we weren't able to fit on one host. We knew our data set needed to be partitioned. And this was one of the more important things that we identified, is that we identified our partition key, the thing that we could split on. And the nature of the data model is that it's only the viewers that need their data set. So we could partition on the viewer key, or the viewer identifier. And by knowing this, a lot of options came up, because we only needed to be consistent on a single partition for a single viewer ID. So given with that, we stuck with the storage-heavy approach, and we needed to grow over multiple hosts. So there's really only one thing that we could do. That's throw hardware at the problem. So we knew we had to throw hardware at the problem, but we needed a new database, we thought, because we thought that, okay, if we have multiple machines, we need a database that can live on multiple machines. Relational databases can live on multiple machines, but we saw that this was in 2009. We saw a lot of new technology show up on the market that had promises of just making partitioning a non-issue. And so we evaluated a little bit of the market, but we also evaluated our workflow and how our workflow would integrate with the databases that we were looking at. Ultimately, when you have data in one form and you need to get it to another form, you're going to be applying this age-old technique of an ETL. This is fine. This is eventually consistent in its core because each of these steps happen in different transactions, and or could happen in different transactions. And for us, the extract was taking the changes as they were happening. The transform was finding those edges to materialize first, and it was the load part that we were having problems with, because we needed to write enough edges. So this is in the orders of hundreds of thousands a second to materialize our index, and we needed to load them in a way that was reasonable across multiple hosts. But what we really wanted was to take advantage of our write hotspots and write everything into memory, and then take advantage of our secondary storage and read everything from disk. And somewhere in between, we didn't want to have to do any work. And this is where we had this dream of, like, what if we could do this? And so we started to evaluate our databases based off of whether they can fill in the magic happens part. And it turns out we found one. So Cassandra has this baked in, but it also had a lot of other properties that were quite beneficial. So being ignorant that we actually had a disk problem, we decided to throw Cassandra at it because it aligned with our data model, and it also offered some conveniences to make our ETL simpler. So Cassandra is eventually consistent in its core. So you've probably heard a lot about the CAP theorem, and Cassandra is in the AP section of the CAP theorem. And every observer, every reader on any node will see the writes that happen even on other nodes eventually. Every node is a master and a slave, so you can connect to any node in your database cluster and read and write to it. You can think of it as like a distributed hash table where you where the writes will get routed to the right host. And there's well understood multi-data center replication. So I believe later in the track, Adrian will talk about how Netflix achieves this with multi-zone replication, which is the same thing as multi-data center replication, multi-zone, multi-region, and and writes are distributed. So as the writes come in, we can split out and avoid those hotspots by distributing our writes across different nodes in the cluster, because you can write to any single one. Cassandra also offers this. So the beautiful nature of our write path with that sequential, with the sequential writes, nice ordered data set, and then sequential reads as well, means that it gives us the promise of no more trips to Milan. Seeing this, I just imagined, okay, yeah, seeks can get under control. But how Cassandra does this is an understanding of its data model and its storage model. So first, to start with Cassandra's data model, which is important to understand to know how Cassandra turns its data model into on-disk storage. And being an abstraction over the storage layer, we first need to understand what kind of abstractions we have to work with. So I've never liked SQL. When I started writing SQL statements, I tried to do this. So I imagined, okay, I have a little bit of data over here, a little bit of data over here. I make the same schema, and then I want to choose which data I'm going to query from. And this has always bugged me, because conceptually I group my partitions in tables mentally, and I want to select which table I'm looking into. So I didn't have any theory about why this language doesn't allow that, but I've always found it annoying. But if we could do this, and we could create 20 million tables, then partitioning is a no-brainer. We just select the users out of each of the user IDs tables, and that would have been great. Oh yeah, and Cassandra, yeah, Cassandra has this model baked in, but I've also wanted to do this. So I didn't know about the entity attribute value pattern, I guess, where you can create a table and then you can, with that table, you can create arbitrary attribute sets. I always wanted to know what attributes I would have available, and so I'd make these super wide tables. I mean, this was a long time ago. I make super wide tables and then say, I want that column, and that column. I want to know what columns are there, so I'm going to make a very wide table. But again, you can't do this with SQL. But even if you could do it in Cassandra, there's a trade-off. In Cassandra, you don't get a flexible order by statement. You can only order by your columns. So this is okay. It just means you have to pick your columns carefully. Yeah, that's about it for this kind of butchering of the SQL metaphor. So if we look at the actual terminology, you can think of the data model in Cassandra like a giant matrix. You have row keys, column names, and then the values. And at the intersection of the row key and the column name, you can find your value. And the important difference when considering this data model versus a relational model is that you can only scan over the columns. You don't scan over the rows. And in Cassandra, the order in which you scan over the columns is defined in your schema. So it's like setting that order by statement, but up front. It's possible to model a data set like you would with a relational model. Like if you were to do a users table, you just pick some column names which are stable. So you can have your name, your avatar URL, your email, and this would be fine. But what you sacrifice is that you can't scan, give me all the rows that have a first name of Bob. Cassandra does have secondary indexes. I'm not going to go into those. But this would be a typical entity modeling in Cassandra. But Cassandra can do a little bit more. So if you use the same key as your row key in your column name, you could easily model an adjacency matrix. And with this, you can model a directed graph. And so the columns just grow, the rows grow, and you can scan over, give me all the outbound edges that I have for any given node. And it's also possible to model our existing activity stream. So if we had a globally consistent sequence generator, which was generating those sequence IDs, we could use the column comparator and order our columns in the same sequence order that we had in our relational store. But if we didn't have that globally consistent counter, we could end up creating duplicates. And it's not as important with our data set, but we decided to model it slightly differently to make the duplicates impossible. And we did this by using the clock of time. But even time can have duplicates because not all clocks are unique. So to make them unique, we encoded them as UUIDs. So it's a variant of version 1 UUIDs where the high bits are where the timestamp lives, the low bits are where the uniqueness lives. So this is NoSQL for me. NoSQL for me is when you model your data, how you want to read it. This is how we're going to access it. We're going to access it in the order of time based off of our column comparator. And we're going to create a very sparse matrix of this. And we're just going to find the row, find the columns, and we'll be done with it. And I think most of the NoSQL databases provide means to have finer control over your access patterns based off of how you model it, your data in the database. But for writes, we need to understand Cassandra's storage model, which is unique. It's different than InnoDB's. But first, we'll get a little bit of the partitioning out of the way. I'm not going to go into depth about partitioning. It's one of its strengths, and it has a lot of coverage, so you can read up about it later. But the quick overview is that for any given row key, it only uses the row key and then finds a host to store and retrieve that row from. It can be more than one host if you have redundancy. And we use the random host partitioning, meaning that any given row key could be on any host, but is predictable. This is why we can't do row scans, because the row keys may not be sequential on each of the nodes. So the storage engine in Mysql, in Cassandra, is based off of a section in the Google's Big Table paper, which splits the problem exactly where we would like to have it split. So for writes and for hot reads, the primary storage is used in a data structure called memtables or memory tables. These are, you can think of them as just hash tables. And for secondary storage, for our writes and also our cold reads, Cassandra, or the Big Table paper, introduces the concept of sorted string tables. The sorted string tables are where the magic happens. Because if you have a sorted data structure, you can actually infer quite a bit. Your searches into it become a degree simpler in complexity. And the sorted string table allows you to maintain those sequential reads and those sequential writes. So in memory, as the writes are coming in, they're coming in any order. They could be any row key, any column name. It doesn't really matter because they're just going to primary storage. They're just going to RAM. And so if you have a read immediately after a write, you don't even hit the disk. Cassandra is durable, so it'll commit to a commit log before actually committing to the write or the memtable. So it's still fast to accept writes. But when that table fills up, and it will fill up as you're adding stuff or adding changes, it periodically needs to flush out of RAM. And this is where Cassandra and also HBase will take the memtables, sort them off the row key, then sort them off the column names to create a stable sorted structure. And then it'll take that and just sequentially write it to disk. And then it'll start with a new memtable. It's important to know that nothing's overwritten on disk. So in the B tree, InnoDB spends a lot of work reusing portions of the page, reusing portions of the pages that the leaves. It makes sure that, like, if you run out of space on the leaf, it'll add a new one. It does a lot of magic in place on disk, and that keeps the data set pretty dense. Here, it's just flushed out. But what that means is that as you're flushing memory tables out to SSTables on disk, you're going to be generating a lot of SSTables because it's only going to be what you were storing in RAM. And this could be 100 megs tops. No, not even that. I think we're at 2 megs. So, but we actually flush at even smaller sizes. So, so what you end up with is a directory full of SSTables. And when performing a read, your columns could be living in more than one table. And so Cassandra keeps some bookkeeping around of what columns are and what rows are in which SSTables, and then it needs to consult all of them to satisfy your read. So you can see if there's really not much difference. If we had all these SSTables on disk, this would be very similar to having all of our page splits in our B tree, and we would be we'd be seeking all over the place to try to satisfy a read. So Cassandra has a compaction phase, which will read which will read a set of SSTables in. Since they're already sorted, the merge is incredibly efficient, and it'll flush that out sequentially. And this is a constant background process that happens that converges the SSTables to reduce the number of tables that are needed to be consulted before a read can be satisfied. But even so, it can't keep everything compacted at the same time. So you would think that you would be just trading seeks in the B tree to seeks across the SSTables. For us, we have a maximum of 20 SSTables that we consult for our dashboards. So this is from a couple days ago, a histogram of number of SSTables consulted for all of our reads, bucketed by the number of SSTables. The important thing to note is that the trend goes left. So the trend in Cassandra is to reduce the number of seeks, reduce the number of tables that need to be consulted or leaves that need to be consulted, wherein the way that we were using the B tree in MySQL, that trend was the other direction. So it's 2 seeks per SSTable, and at 20 SSTables as a maximum for satisfying our reads, we now know our upper bound. Our upper bound's 40 seeks. And with this, we have a much more confidence. But even at 40 seeks, one would think consulting all those tables for cold reads would increase latency. So even out in Milan land, where we're consulting many of their tables, we're still much better off than we were with MySQL. So we're under 200 milliseconds in our upper bound for satisfying a dashboard read, and these are our cold reads. These are the reads that for somebody that hasn't logged in for a while that needs to pull that up into RAM. Our average is 20 milliseconds, and that's still a couple trips to Milan, but it's much better than we were doing before. And writes are a whole different unit of measurement. So when you see a distribution like this, you know you're doing it right because it's nice and tight. You don't have any outliers. You can just pretty much ignore the units because you have a predictable distribution. But for us, this is in microseconds. And at this load, our cluster can easily take bursts of 75,000 writes per second, so 75,000 materializations of edges per second. So we did it. So we've addressed some of the concerns about partitioning with Cassandra. We're accepting a lot of writes from all of these edges that we're materializing, and we've stabilized our load times. And with the partitioning techniques that Cassandra gave, we were able to actually perform a live data center migration. So we set this up before we had moved from England to Amsterdam, and this database or this database cluster was the only thing that was online the entire time during the transition. We also could accept writes from multiple data centers, so we were writing in Amsterdam, writing in England. And you may find this amazing, but those metrics on those latencies were from a cluster that's running in EC2 with a notoriously slow I/O times. So both with Cassandra and in the SSTables and InnoDB with its B trees, they're using the disks effectively, but in different ways. So Cassandra accepts random writes very well, much better than InnoDB, but as InnoDB is creating random writes by maintaining the index. But once that index is established, InnoDB does much better for performing reads because it can traverse that tree with fewer hops than the number of SSTables that you need to consult. But it hasn't been such a great experience with Cassandra. We spend a lot of time on operations of our clusters, and we have about like 5 to 10 hours a week of just babysitting it. There's alerts that go off that where nodes can't communicate. It's distributed, and we understand why it's happening, but we still have to respond to it. And periodically, we have to intervene and say, yeah, you need to go down for a while, or you've been down for too long, and we're going to bring up another. And as a result, we haven't quite worked out those kinks, but if you do go with Cassandra, you can expect trading bit of time for operation of anything larger than a 5-node cluster. And yeah, in hindsight, we know now how exactly we would have built it with MySQL. So the problem that we were having of our index splitting could easily be mitigated by optimizing our table, periodically rewriting the entire B tree, and splitting that up into smaller chunks so it doesn't create outages, or buffering up our workflow, our ETL and RAM, before writing out to MySQL to avoid being down during that time. So to wrap this up of how we fit our database to our data model, we did a lot of right things, a lot of smart things along the way. We found our natural partition key. We isolated our read path from our write path. We identified the volume and the access patterns, both for our read and write loads, whether they were sequential or random. And we developed a sympathy for the materials that we were using. But most importantly, we never forgot our goal of delivering a product that kicked ass. So we architected first without fully understanding what our building materials were, because we assumed that our database is going to hide that from us. So whether you try to fit your data model to your database, or whether you choose to fit your database to your data model, ultimately the success of your design and the ability to hide your ignorance to the public is really based on how well you understand the materials that you're working with. So that's it. Thank you.